Hey guys, not the circumstances I would have liked to be sharing this lesson with you, but we're forced to do this remotely for a few days. So I wanted to put together a quick little video providing some instruction to help you be successful with this lesson, lesson 2.2, dealing with limits involving infinity. So let's take a look at it together. Here's our objectives in this lesson. We're going to take a look at that squeeze theorem. We can apply that squeeze theorem also with limits at infinity. And then we're going to also look at some asymptotic and unbounded behavior of functions. So when functions have asymptotes, how in some of those situations, specifically when they're vertical asymptotes, how they have unbounded behavior. And what do we do when we're representing the limit as x approaches some value and the function appears to approach infinity? And then also we'll look at the end behavior of functions. So here we'll deal with infinity as the bound of the limit. So as x approaches infinity or x approaches negative infinity, well, how does this function behave? Okay. So finite limits as x approaches positive or negative infinity. So they say the symbol here for infinity does not represent a real number. We need to be very, very clear on that. This is an area that we've talked a little bit about already. If we're trying to evaluate a limit and the limit approaches positive or negative infinity, technically those are situations where the limit does not exist. However, we can be a little more specific and we can state that the limit is positive or negative infinity if both sides agree, if the left-hand limit and the right-hand limit agree on that. So we use infinity to describe the behavior of a function when the values in its domain or range outgrow all finite bounds. For example, it says when we say the limit of the function as x approaches infinity, we mean the limit of the function as x moves increasingly far to the right on the number line. So again, here we're dealing with as x approaches positive and negative infinity. What we mean by that is clearly infinity is not an attainable number. We're just saying, what's the limit of this function? How does this function behave? What are the outputs doing as x gets really big, ridiculously big? That's what we mean when we say the limit of the function as x approaches infinity. Likewise, when we say the limit of the function as x approaches negative infinity, we mean what's the limit of the function as x gets really small, as x goes far left on that number line. Okay, that's what we're talking about. Specifically in these situations, we might run into a horizontal asymptote. It doesn't have to be, but it says the line y equals b is a horizontal asymptote of the graph of the function of what function? That function f of x. If either, key information there to read this very clearly, if either, and then there's an or statement, so both of these don't have to exist, but one of them does if we're going to have a horizontal asymptote at the line y equals b. That limit as x approaches infinity of the function has to be b, or the limit as x approaches negative infinity of that function has to be b. That's when we know that we have a horizontal asymptote. Now, we've seen functions that have horizontal asymptotes before. This isn't the first time. We've looked at things, say in pre-calculus, that maybe the function looked like a different color to distinguish between the coordinate plane, but we've seen a function maybe that does something like this, where, yeah, it seems like there's this idea of this horizontal asymptote running right down through here. Well, yeah, that is a horizontal asymptote, and I think visually we can agree with that, but look at what's going on. The limit as x approaches positive infinity, as I follow this graph, as x gets really big, far to the right, what is the function value approaching? The function value maybe is approaching this concept of this value of b. So that's as x approaches positive infinity, we see that it equals b. Well, it also exists in this function that I've drawn here. It doesn't have to, but in this specific example, that if I follow x on this function as x gets further and further negative, further to the left, what is this function doing? It seems to be approaching the same value, okay? And so we've again, we've seen horizontal asymptotes before, but this is a limit definition to a horizontal asymptote. Horizontal asymptotes, another thing that I mentioned in pre-calc last year, are where we're studying the function, what behaves at their extremes. How does the function behave at their extremes? If one or both sides of the function at its extreme approaches this value, we could say it's a horizontal asymptote, and we can use the limit notation to represent that. So it says, use the graph and tables to find the limit as x approaches infinity of f of x and the limit as x approaches negative infinity of f of x. So they're going to give us here an example, and then part C, identify all horizontal asymptotes. So they want both limits as x approaches positive and negative infinity, and then identify all horizontal asymptotes. So what's the function? Here's the function that's given to us. F of x equals x plus 1 all divided by x. Let's take a look at this graphically. I'm going to go ahead and exit out of the PowerPoint and pull up the graphing calculator because they say use graphs and tables, so we'll look at both of those. Okay, so coming on out, we'll go in here. Let me double check what the function was, x plus 1 over x. So y equals, I've already got a fraction in here, but I'll go ahead and clear it out. X plus 1 all divided by x. I'll double check one last time. Yep, that's what it was. Okay, I'm going to go ahead and zoom 6, give us a standard zoom window, and there's a picture of the graph. Hey, this looks pretty similar to something that we've looked at just recently. So as we look at this, again, there are 3 questions that were asked. What is the limit as x approaches infinity? What is the limit as x approaches negative infinity? Well, again, if we trace this graph, following as x gets bigger and bigger and bigger and bigger and bigger, where does this appear to be limiting out at? Maybe you have a guess about 1. We'll have to look. Okay, and same thing, they also ask what's the limit as x approaches negative infinity? Maybe he's limiting out at the same 1. Okay. And thus we think maybe that there's a horizontal asymptote at 1. Let's take a look at the table real quick to see if that shows the same kind of information. So second graph to get my table. It's probably not necessarily where I wanted to see. I've got some nice fractions in there, that's pretty sweet, but let's go ahead, second window table set. Let's start our table at, let's first look at as x gets really, really big. So as x approaches positive infinity. So let's go way out. Let's start at 100. I don't know. Way is relative. Change in table. Actually, let's even go to 1,000. We're going to do our change in table to be 100. And let's go back to our table now. All right. All right, so table, sorry. I was not used to my table showing the fractions, but that's fine. And it makes sense if you think about the equation. What did I have? I had x plus 1 divide x. So as I go out to a million, I'm going to have a million on top, or sorry, plus 1. So 1,000,001 on top divided by a million. That's just a smidge above what the denominator is. So something divided by itself is essentially 1, right? Something divided by itself is 1, but something slightly bigger than itself divided by itself is essentially 1. And so that's really what we're dealing with. Look at these values, right? We're going to get closer and closer to 1. Real close to the origin there, 1 plus 1, well, that gives me 2 divide 1. Okay, you can see why we would be further away there, but as I get further and further and further out, that doesn't have as much of an effect. Also, think of it this way. I could have, this is more algebraically, I could have said, well, since we were dealing with this function, I can simplify this function as split up the divide by x as x over x plus 1 over x. Well, x over x makes 1, and as x gets really, really big, what does this fraction turn into? 1 divided by a ridiculously big number is essentially 0. So I'm saying 1 plus 0. If I was to trace out the limit and apply some limit properties, we'd see, hey, this limit is 1 as x approaches positive infinity. Okay, so I think the table and the graph both seem to agree that we are approaching 1 as the limit of that function as x approaches positive infinity. Negative infinity, again, we've already looked at the graph. You can make a slight change here, go second insert, put in a negative right there. Okay, delta table being 100, and we go second table. And now once again, as I keep going further and further up, okay, we're approaching 1. As I go further and further into the negative, I'm approaching 1, but from the underside, right? Look at all of these values, because my values for x are negative. That negative plus 1 divided by that negative number is going to be slightly smaller than 1, okay? So, but I think you can agree, the further and further out, they're only 1 off from the numerator to the denominator, and that's going to cause those to be closer and closer to 1, okay? So, based on that previous definition, we can say we just learned that the limit as x approaches infinity of this function, can't remember what they named this function, but let's see here, did they give it, they named it f of x. So the limit as x approaches infinity, not 0, of f of x seems to be 1. That was what we looked at first. Then as we just looked at the limit as x approaches negative infinity of f of x, it also appears to be 1. Well, remember, the horizontal asymptote definition said that either one of these cases, if we can identify what the limit as x approaches infinity of any function is, that ends up being our horizontal asymptote. They both don't have to be the same. I could end up having 2 horizontal asymptotes potentially. But what we learn here is that a horizontal asymptote occurs horizontal. All horizontal lines are y equals at y equals 1. So that, I think, answers their 3 questions. All right? So let's head on back to that PowerPoint, and I think they will agree. The limit as x approaches positive infinity was 1. The limit as x approaches negative infinity of the function was also 1. And identify all horizontal asymptotes, y equals 1. And there was the graph essentially we looked at as well. Okay. All right. Now, that sandwich theorem can also apply for limits as x approaches positive and negative infinity. It doesn't have to just be as x approaches c, some value. It can be specific to positive and negative infinity. For example, this is asking us to confirm this, it says graphically and using a table of values. But let's take a look at this. Let's think about this more analytically and changing the way that the directions are saying. Because what do I know about cosine? Cosine is a periodic function, a trigonometric function, that always oscillates back and forth between what numbers? Negative 1 and 1, right? So if that's the case, hopefully you'd agree that cosine x over x as a function is always between negative 1 over x and 1 over x, right? All 3 of these functions have x in their denominator. The numerator here, cosine, always goes between negative 1 and 1. It's at its smallest when it equals negative 1, but it's at its largest when it equals 1. But every other time it's oscillating back and forth between there. Okay, so if that's the case, remember what that squeeze or sandwich theorem stated is that if the limit as x approaches, say they're asking positive infinity, so we'll do that. The limit as x approaches positive infinity of negative 1 over x equals L. The limit as x approaches positive infinity of 1 over x equals L, because that's what this function that I'm interested in, its limiting value as x approaches infinity is. If both of these have the same limit, then this function squeezed in, sandwiched in between these two, has to have the exact same limit. Okay, and so, well, think about your 1 over x function. Okay, 1 over x, well, we've got 2 functions, 1 over x and then negative 1 over x, but since we're dealing with as x approaches positive infinity, if x is 1, so I'm going to look first at this one on the bottom. If x is 1, y is 1. If x is a half, y is 2. If x is a third, y is 3. If x is 2, y is a half. If x is 4, y is a quarter, right? And so we know that this is what the 1 over x function looks like. And if I'm looking at what is the limit as x approaches infinity of 1 over x, so as I go this way on it, where am I approaching? 1 divided by a really, really big number is 0, right? Approaches 0 anyways. Likewise, negative 1 over x. As x gets really, really big, 1 divided by 10, 1/10, but negative, so negative 1/10, so 0.1. 1 divided by 100 is, but negative, is negative 0.01. 1 divided by 1,000, but negative is 0.001, right? What am I approaching as x gets really, really big of this function? I'm approaching 0 again, but just from the negative side, so this equals 0 as well. Well, if the limit of these two functions, that this function is always sandwiched or squeezed in between, is 0, then we know that the limit of this, so this thing right here, altogether has to be 0. Okay. And again, we can look at this graphically or using a table of values as well, so let's go ahead and do that real quick, more actually answering the question by their directions. So I'll go back to the graph here. We got cosine x over x. So y equals, we've got cosine x over x. I'm in radian mode, which is great. I'm going to go ahead and, let's just do zoom 6 again. It's already there, so graph. Okay, so what's happening here? Yeah, I think that graph seems to agree with what we just talked about, and that being, as I follow this graph as x gets really, really, really big, what happens? Well, it seems like it's oscillating back and forth. Well, that makes sense, it would oscillate back and forth. The numerator cosine x oscillates back and forth between negative 1 and 1, so it's oscillating back and forth between signs, positive and negative. So what we see happen as x approaches positive infinity, which is, I know, way, way, way out there, is that this seems to limit out at 0, seems to essentially flatline at 0. Likewise, as x approaches negative infinity of this function, seems to do the same thing, but that direction where it limits out at 0. Okay, so there is that part. And if you like the visual, I guess I could put 1 over x, 1 divide x, oops, 1 divide x, sorry, 1 divide x and negative 1 divide x, and graph those alongside, and you'll notice that, yeah, our function is always, that blue function is always squeezed in there in amongst the black and the blue, red functions. Okay, so that might be helpful there. It also asked us to look at this from a table perspective, so I can do that by, let's go ahead and just, I'm going to set my table set. I'm going to start at 0, but I'm going to change, sure, by hundreds. So second table. All right, so I'll go up here. You can see, okay, as I have x approach negative infinity, so I'm going that way, what's happening here? I've got negative 0.009, negative 0.002, this is scientific notation, but all you see is we're oscillating back and forth. I might need to go quite a bit further to see that we actually do get closer to 0. You can see here 0.009, 0.002. If I keep going up, we'll just notice that if I were to play with scientific notation here, that these are all getting closer and closer and closer to 0. And likewise, as x approaches positive infinity, so now I'm going this way, you would notice that all of these are getting closer and closer, those y values, that is, to 0. Okay? Again, they're still oscillating back and forth there though. That's why you see some positive and some negative. Okay, so I think that's what they're wanting you to see by looking at this graphically. Okay, so yeah, we found the limit. We think that it's 0, and if that's the case, the graph and table suggests the function oscillates about the x-axis. Thus, y equals 0 is a horizontal asymptote. And so this kind of dispels some people have a prior thought that horizontal asymptotes, the graph can never touch or cross. That's not true with horizontal asymptotes. Horizontal asymptotes, a better definition is, this is how the function behaves way out at the extremes. It's kind of an end behavior description of the function. If I were to zoom way out and just focus on the ends of this graph, all you'd see is this horizontal flat line at the origin, or at the x-axis. Okay. All right, and again, we can say that, again, because of that horizontal asymptote definition, if I know that the limit as x approaches positive infinity of some function equals some number, that's what its horizontal asymptote is. Okay. Don't need to spend a ton of time with this. These properties of limits as x approaches positive and negative infinity are the exact same properties, really, that we saw as x approaches some constant. So the sum rule, all that it's saying there, the limit of a sum is the sum of their limits. So if I have trying to take a limit of a sum, I can split that up and take the limit of each of the individual functions that are being added. Same thing applies to the difference. Same thing applies to a product. The constant multiple, if I am taking a limit of a constant times a function, I can pull that constant on out and say that that's equal to the product of the constant and the limit of the function. Okay? And likewise with the quotient rule, the limit of a quotient of functions is equal to the quotient or the division of their limits. Okay? Provided that the limit of the denominator function is not 0. And then the power rule as well. Okay, so all of those properties that we really spent a little bit of time working with, and we started actually putting to use when we were evaluating limits at a real number. Okay, so if the values of a function f of x outgrow all positive bounds, so this is now dealing with infinite limits, as the title says, as x approaches a. So we're not talking at this point as x approaches positive infinity or negative infinity. Now we're talking that the actual limit grows without bound. So if the values of the function outgrow all positive bounds as x approaches a finite number a, we say that the limit as x approaches a of the function is infinity. And we say infinity because it was outgrow all positive bounds. If it was outgrow all negative bounds, as you see here in the next sentence, we'll say that the limit as x approaches a of that function is equal to negative infinity. Now, can our limit really ever be equal to an infinity or negative infinity? No. This specifically is that area that we've talked about a little bit already in class of, by technical definition, a limit is a real number that this function's outputs is approaching. And as we get, closer and closer and closer to this value, in this case a, and so technically the limit doesn't exist. However, if both sides, and this is key, it doesn't necessarily say that right here, but if both sides agree that we're approaching positive infinity, in that case we can say that the limit as x approaches a is infinity. Okay, it's not bad form to say that. And this is actually the definition of when we have a vertical asymptote. Okay, so the line x equals a is a vertical asymptote of the graph of the function f of x if either, there's really actually 4 things listed here. The limit as x approaches a from the right of the function is positive or negative infinity. There's 2 things. Or the limit as x approaches a from the left of the function is positive or negative infinity. So if there is some finite number a that we're approaching and our function values are growing without bound, then we can say that there's a presence of a vertical asymptote. Okay. So this example with vertical asymptotes asks us to find the vertical asymptotes of the graph and describe the behavior to the right and left of each vertical asymptote. Okay, so here's that function, f of x equals 8 divided by 4 minus x squared. Okay, so let's take a look at this function together. 8 divided by 4 minus x squared. So I'll come back over to the graph, y equals 8 divided by 4 minus x squared. And then we'll go ahead and hit graph. Okay. So where does it appear? You guys have a little bit of an understanding, I think, about a vertical asymptote just from the pre-calc days, but now as we talk notation, are there certain values of x where this graph appears to approach, the function values of the graph approach positive or negative infinity? Well, as I trace this graph, I'll start over here, trace this graph. Where are these function values going? Hopefully you're saying negative infinity. It just keeps going, right? And so what is this value that we're approaching, the function value is approaching negative infinity? It appears negative 2, so what can I write? I can say, well, the limit as x approaches negative 2, from what direction? This is from the left, of this function is what? Negative infinity. Negative infinity. Well, is that what the function is doing as x approaches negative 2 from the right? Well, let's see. The limit as x approaches negative 2 from the right of the function. Okay, as x approaches negative 2. No, that's going off to positive infinity. Okay, so I'm not going to ask you probably what's the limit as, or maybe I could, but what's the limit as x approaches negative 2 period of f of x? If that was the case, in this situation, you'd have to say does not exist because the left-handed limit and the right-handed limit do not agree. Okay, but I can say the left-handed limit of this function is at negative 2 is negative infinity, and the right-handed limit of this function at negative 2 is positive infinity. Okay. So, I don't remember the statement for a vertical asymptote wasn't that both of these existed. It was that one of these existed, right? There was that either and or word in there. So what can I say? I can say that we have a vertical asymptote at x equals negative 2 because of either one of those statements. The fact that I had both of them, it didn't matter. Okay. Now, is that my only vertical asymptote? I don't think so. There's also, I believe, a vertical asymptote right here. Okay, so let's take a look at what the limit notation would look like there. The limit as x approaches, what value does that appear to be? 2. Let's do it from the left first of this function. So as I follow this function from, to 2 from the left, where am I going? Positive infinity. As I follow this function from the right to 2, where am I going? Oh, negative infinity. So the limit as x approaches 2 from the right of the function is negative infinity. Again, I don't need these two to agree unless I'm asking what is the limit as x approaches 2. Unless I'm asking what we call that two-sided limit, they don't have to agree. And that doesn't negate the fact that we still have another vertical asymptote at, we can say, x equals 2. Again, because either one of those I had as the case. Okay, so that's how you can look at the graph and help identify vertical asymptotes and the limit notation that represents that. Okay. All right. So back here, I'm gonna get close to finishing out things for the day. We saw that the values of the function approach negative infinity to the left of x equals negative 2. The values of the function approach positive infinity to the right of negative 2. and then values of the function approach positive infinity to the left of 2 and negative infinity to the right of 2. So there's all those limit notations that we already said. So there's vertical asymptotes at x equals -2 and 2. And there is the graph that we looked at. Okay. So next we're going to talk about this idea of end behavior model. A function g, it says, is a right end behavior model for the function if and only if, there's that biconditional statement, the limit as x approaches infinity of f of x divided g of x is 1. Okay, so basically, if you divide two functions and you get 1, what you're kind of saying is that both of these functions are pretty much the same thing. Think of it this way. If I was to take this x to the 6 plus 5x squared plus 7, and I was to divide by x to the 6th, would you all agree that I could rewrite this as 1 plus 5 over x to the 4th plus 7 over x to the 6th? Okay. Well, if I wanted to take a limit as x approaches infinity of this, then that would equal the limits as x approaches infinity of that thing. Well, according to our properties of limits, this would equal the limit of a constant is a constant, so that's 1 plus, think about this fraction, as x gets really, really big towards infinity. 5 divided by a ridiculously big number to the 4th power. That approaches 0. This limit approaches 0. And so I would be getting this, which is then 1. So what am I learning from this? I'm learning that x to the 6th right here, according to this definition, x to the 6th is a right end behavior model for this polynomial. Because as I go really, really far out to the right, all of this other stuff out here essentially goes to 0, and these two things end up being pretty much the same thing. Now, this also happens to be the case if I were to do this as the limit as x approaches negative infinity of the same two functions, because that whole negative infinity doesn't come into play until I start evaluating these two limits. And so 5 divided by a really, 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 really big negative number raised to the 4th power, that essentially goes to 0 as well, and same thing there. So anyways, the whole goal of this is to help us realize that we can use limits to identify for us a function that serves as a right end behavior model or left end behavior model. And more often than not, what we're looking for and what we're dealing with is going to be some type of a polynomial function, and we just need to realize that essentially this monomial first term can serve as a right or a left end behavior model for that function. Okay, and so this is kind of where they generalize that idea with polynomials. If one function provides both a left and right hand end behavior model, it is simply called an end behavior model. So in general, g of x equaling a sub n x to the n, notice that's the first term of the polynomial f listed here, is an end behavior model for the polynomial function as listed there. So overall, all polynomials behave like monomials. Okay, and I think there's a good example in your book of showing visually the graph of that. When you zoom in really close on two functions that have, I think they were like x to the 4th and then x to the 4th plus blah, 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 really close to the origin, okay, you see some of the differences, but if you zoom out and you just look big picture at these two functions, they really behave the same way. And you can just think of that even in, okay, just taking x squared and x squared plus 1. Okay, yeah, real close to the origin, you can tell the difference between them, one's shifted up. But if I zoom out and zoom out and zoom out, they're going to look like exactly the same functions. So it's asking us to find an end behavior model for each of these. Well, okay, so just in the numerator, because that's a polynomial, what did we learn is a end behavior model for that? Just that first monomial, right? So 3x squared, and I'm going to be careful here of saying equals, because that's not necessarily true. But what we can say is that the limit, that's not a limit, I guess I could say the limit of, as x approaches infinity of f of x equals the limit as x approaches infinity of 3x squared divide 4x squared. Okay, just taking the monomial of each of those. And then, well, 3x squared over 4x squared, that simplifies. That's just the limit as x approaches infinity of 3/4. In class, what do we learn is, according to those properties today, the infinite limit as x approaches infinity of a constant is just that constant. So find an end behavior model, 3/4. So let's take a look at this and see if we can have our calculator show us this. So I'm going to try to remember this, 3x squared minus 2x plus 5. Let's go to our calculator here. Y equals 3, we've got 3x squared, what was it, minus 2x plus 5, minus 2x plus 5, divided by 4x squared plus 7, 4x squared plus 7. Okay, so there's one function, clear, and then I'm just going to graph our end behavior model, 3/4. Now, on my standard window, let me clear some of this other stuff. Sorry, I should have done that for you before. Okay, on my standard window, if I were to zoom in here, zoom in. Okay, right there, zoomed in pretty close to the origin, I can see a little bit of a distinction, a little bit of difference between these two functions, right? However, as I went to that standard window, my zoom 6, that's just zooming out a little bit. You can see that there's a difference, that these aren't the exact same function. That's why I wanted to be really careful about saying equals earlier on, but they are not the same function. But again, end behavior model out here, you start to have a harder time seeing any difference. If I were to zoom out again, zoom out, 3, enter, you have a harder and harder time telling the difference between these two functions. Okay, and that's again because 3/4 is a good end behavior model. It tells us how the function behaves at its ends, just like the function 3/4. Okay. Alrighty. So again, they do the same thing. They say, notice that 3x squared is the end behavior model for the numerator, and then 4x squared is 1 for the denominator. This makes 3x squared over 4x squared, or 3/4, an end behavior model for the function. Okay. So in this example, the end behavior model of for function f, y equals 3/4, is also a horizontal asymptote. We can use the end behavior model of a rational function to identify any horizontal asymptote. And this shouldn't necessarily surprise you, because remember in pre-calc, when we were dealing with horizontal asymptotes of rational functions, we said, well, if the numerator and the denominator have the same degree, to find that horizontal asymptote, all we had to do was divide their leading coefficients. And so that's really what we're seeing here in creating that end behavior model. Okay. All right, one last thing to finish with. It says example of seeing limits as x approaches positive and negative infinity. This is just another way to evaluate, to identify a limit as x approaches positive and negative infinity. Since it's harder to see positive and negative infinity, that's why they use seeing in quotes, we can actually investigate, it says we can investigate the graph of the function y equals f of x as x approaches positive or negative infinity by investigating the graph of y equals f of x of 1 over x. Well, yeah, this makes a little bit of sense, because as x approaches 0, 1 divided by something getting smaller and smaller and smaller and closer and closer and closer to 0, that 1 over that number is approaching positive infinity, right? And so that's why doing this is still really evaluating this, the function as x approaches positive infinity, because that's my inside approaching positive infinity, just like if I let x here go to positive infinity. Okay, so let's take a look at an example with this. It says use the graph of y equals f of 1 over x to find the positive, the limit as x approaches positive infinity of f of x, and the limit as x approaches negative infinity of f of x for the function x times cosine of 1 over x. Well, the very first thing to do anytime you're going to use this trick to help in identifying these, we'll call infinite limits, is let's figure out, well, what is f of 1 over x? Well, 1 over x turns that into 1 over x, and this is 1 over 1 over x. So I believe this ends up being just cosine x over x. Okay? So the limit, let me write it this way, the limit as x approaches positive infinity of f of x is equal to the limit as x approaches 0 from the right of f of 1 over x. So what happens as x approaches 0 of that? Well, we could go, again, it says we can investigate the graph by investigating the graph. So we want to look at what's the graph of this thing doing close to the origin. Okay, well, we can even just start thinking about it, I think, because what's happening to cosine as we get close to 0 from the right? Well, cosine, those x values, remember cosine, let's just take a look at the graph. I think it will be faster if we do that. So I'm trying to think on my toes and I'm struggling a little bit. So cosine x, we've looked at sine x over x. Now let's look at cosine x. There we go. And clear that out. Ooh, let's zoom back in, zoom 6. Okay. So what does it appear? Again, what are we looking for? We're looking for how does this function behave? Let me get back here. What's the limit as x approaches 0 of that function from the right though? From the right. Okay, so if I look from the right, okay, well, here's the graph as well, but if I were to look from the right, as I approach 0, what's my graph doing? Shooting off to positive infinity. What's my graph doing as x approaches 0 from the left? Shooting down to negative infinity, okay? So we go back right here. What's the graph of the function, what's the limit as x approaches 0 from the right? Remember the graph was kind of oscillating back and forth, but then it shot off to positive infinity. And then the limits as x approaches negative infinity of the function is equal to, using this little trick of being able to see infinite limits, the limit as x approaches 0 from the left of this, and that was, again, remember it was kind of oscillating and then shooting off down to negative infinity. Negative infinity. So again, because of utilizing this reciprocal trick here, we can say that, again, overall, the infinite limit as x approaches positive infinity of the function is positive infinity, and the limit as x approaches negative infinity of the function is negative infinity. Okay, so a little bit tricky to think about, but I think if you just truly follow the algebra, it should make sense. When I do that little substitution, I put 1 over x in there. As x gets small, that's just like making my input being really, really big overall. So it really is doing the same thing as x approaching positive infinity or negative infinity. Okay, so anyways, I think that's all I wanted to cover in this lesson. Yeah, so if we were to look at this set of exit test questions, which I know I didn't give you a bell ringer in there, but set of exit test questions, find a power function and behavior model for this. Okay, so in part A, again, remember, we can find an end behavior model for the numerator, and that would just be x, an end behavior model for the denominator, and that would be 2x squared. Well, this simplifies. There's a power or a factor of x in both the numerator and denominator that can be removed, and so you end up with 1 over 2x, okay? And that right there would be a power function end behavior model for the function. So we could call this g of x or something, and that would be a function that has an end behavior representation that this one has as well, okay? So part B, identify any horizontal asymptotes. And remember, horizontal asymptotes are as x gets really, really, really big. So what happens to this end behavior model, which represents this basically, as x gets really, really big? As x gets really, really big positive, that's 1 divided by 2 times something ridiculously big. 1 divided by something ridiculously big is 0. And as x approaches negative infinity, 1 divided by 2 times some negative, really, really big number also approaches 0. So it looks like we have a horizontal asymptote at y equals 0 on that function, okay? And again, I could do that by substituting in here, but I could also just look at this one because this is an end behavior model, and when we're asked horizontal asymptotes, it's end behavior information, right? Who cares what's going on in the middle of the graph? It's what is happening at the end or the extremes of the graph, okay? All right, that's the end of this lesson. That homework assignment is actually when I split this into two days. So hopefully this helps. I know that this is still somewhat fresh with you as we're just getting in and introducing calculus concepts, specifically dealing with limits. But hopefully this provides something for you to be successful in this lesson. And hopefully that we'll be back together again later this week, and any questions you'll have an opportunity to ask, and we can get those things clarified. So thanks again for watching. Hope this helps, and stay safe.